the radius of a circular disc, it's probably in the old book too. I don't know if you can see. So the radius of a circular disc is given as 24 centimeters with a maximum error in measurement of 0.2. First question, use differentials to estimate, not exact, but estimate the maximum error in the calculated area of the disk, and then we'll come back to part B. So let me write this again. So we have a circular disk, and the radius is given to us as 24 centimeters. It says a max error in the measurement of the radius of 0.2 centimeters. Use differentials to estimate the maximum error in the calculated area. So estimate the max error in area. So before we even think of area, let's identify what we're given. Well, this is clear. So this is the radius of the disk. And there is an error. So if this is the radius, what is this?
Is that the error?
Yes. How do we denote the error? Yes.
dx.
Very good. Because I said r for this, I'm going to write the r. If you want to change this to x, that's fine. So it's 24 centimeters, and then dx equals 0.2 centimeters. It doesn't matter. Now, if they were asking us to determine the exact error, what would you have calculated?
dy? Oh, delta.
Right? So in other words, you would have calculated the area of 24 plus 0.2 minus the area of 24. And this would have been the exact error. They don't want that. They want an estimate. What do we estimate delta A by?
dA.
Excellent, brilliant. Thank you very much. So if they want the exact, we have these calculations to perform, but they don't. Okay, now, first let's write on the side what is the area of a disk, and then I'll continue with dA.
Is it 2 pi r squared?
Excellent, but that's a circumference. So it's 2 pi r. The area is pi r squared. Perfect. So pi r squared. So then, what do we know? This is a function of r, right? So can anyone give us the formula for dA? Don't differentiate anything. Just give me the formula. For everyone to see how we determine dA. Okay, what is the formula for dy then?
The derivative of the function
Yes, times
dx.
dx or dr. So in general, it's f prime of x dx. Now our function is the area, and our dx was denoted by dr. Same thing. Good. So now let's differentiate this and put it here. So then dA equals, can anyone differentiate this for us?
Two pi r.
Excellent.
times
the differential of r. Exactly. That's what they want us to calculate. That is the estimate. So then dA will be 2 pi 24 times 0.2. Whatever that is. I have the calculator up. So what is that? 28. I don't need a calculator for that. 48, of course, right? 48 times 0.2. That is 9.6 pi. Measurement unit. So the error,
Centimeters squared.
excellent, because it's the error in the area. That's it, done. In part B, they're asking us, what is the relative error? So the relative error is always error over original. In other words, it's dA over A. So we know that dA is 9.6 pi. We know that the area is pi times 24 squared. So it's centimeter squared over centimeter squared. There is no measurement unit. So I simplify, and I get 9.6 divided by 24 squared. What did I get? 0.00167. And they're also asking, what is the percentage error? Same thing. Just move the decimal point 2 spots, 1.67%. So this is percentage error. This is the relative error. Any questions? Any questions? Okay, so let's finish.
I actually
Yes,
have a quick question.
please.
Sorry. So when it, like, I noticed on the homework, it says when it asks for, like, I'm just like clarifying which formulas we would use. So when it asks for dy without giving us anything, we will use dy equals f prime of x times dx.
Perfect.
And then
Yeah,
another
remember
question
last time
said-
we put them side by side. So one side was the derivative and the other one the differential.
Yeah, but my question was when it says using like linear I forget, like
Linear approximation, we haven't talked about that yet.
Okay, but that's when we like guess the error, or like we you know, like if it's 1,001, then we'd guess it was 1, or if it was 100.5, we'd say that d of x would be 0.5.
So it depends on the function. It's a very good question. So when we had the cube root of 1,001 or whatever it was, if I remember correctly, so if it's the cube root of 1,001, then it's very clear because the function says so. Then x equals 1,000 and the minor error is 1. Now, if I have, for example, 1 divided by 4.002, then obviously x is 4 and dx is 0.002. So it depends on the function, it depends on the question. So there is...
Yeah, but we would make that estimate anytime it asks us for linearization. And when it says just
we haven't talked about the linearization yet. So are you talking about approximating? Use a linear approximation or differentials. We only talked about differentials. It's the same idea. It's really the same. You're right.
So there was a question on the homework that was like, I think it was the square root of 100.5. For that one, I think it said, maybe I'm like remembering it wrong. I thought it said linearization.
Use a linear approximation or differentials to estimate.
Oh, okay, approximation. So when it says approximation, that's when we make the guess. But if it doesn't say approximation, then we just do dy equals f prime x times dx, and we don't put a value in for dx, right?
No. So when you are asked to find the differential, of a function, then you write f prime of x dx because that's dy. If you're asked to approximate this, you still have to start, the idea is delta y is approximately dy. And from here, we get f of x plus a little bit is approximately f of x plus f prime of x dx. But the linear approximation or the differentials is really the same thing.
Okay, yeah, I just wanted to double check when I approximated and when I didn't. Okay,
Right.
Thank you.
Thank you. So for this, in this situation, f of x is the square root of x is 100, and the minor error is 0.5. And the f prime of x is 1 over 2, the square root of x, which means that this piece is the square root of x, which is 10. This piece is 0.5. And when you plug in here, 100 is 1 over 20. So this one is 1 over 20. So then we have 10 plus 0.5 over 20. I have to multiply top and bottom, no decimal numbers in a fraction. So it's 5 divided by 200, or 1 divided by 40. So 10 plus 1 over 40. So this is 401 over 40.
Okay, thank you. That is what I got. I was just like a little confused because like for some reason I couldn't remember just doing dy equals f prime of x times dx. So when I first saw that, I was trying to approximate for like the first question, and then I like read through the book and refreshed my memory.
Okay.
So okay, thank you.
Thank you. So always before you do anything, always look at what we did in class, and the video if necessary. Is that okay now?
Yeah, thank you.
Thank you. So now let's go back to that linearization. So this is f of x. This is the tangent line. And we know that this is point P. And let's say the coordinates of P, of course, are a, f of a. We know you already told me last time that the slope of the tangent line is f prime of a. Sorry about that, I forgot to turn off my phone. So because of that, then we have y minus y1 equals the slope times x minus x1. I need to determine, to find the equation of this line. So y1 is f of a, because that's the point, a, f of a. x1 is a, and the slope is obviously f prime of a. So I have all the parts. So then I'll say that a y minus f of a equals f prime of a times x minus a. And I will move f of a to the other side. Plus f prime of a, x minus a. This is also denoted by L of x. It's a linear function, that's why it's denoted by uppercase L, linear function. So this is the equation of this line. And why is it so important? Is because near A, I'm not saying here or here, I'm saying near A, if I use the function to evaluate and get exact, of course, or I use the tangent line like we just did, instead of plugging in the function a and a little bit or a minus a little bit, we can plug it in the linear function because the approximation will be very good. So this is what it's called, linearization of f of x near a. So we say also that f of x is approximately f of a plus f prime of a, x minus a. It's not equal. This is the name of this line. But the function itself does not equal the function value, these function values. And now this is called the linear approximation of f of x at a. And now let's see how we apply this. Find the linearization L of x, let's say for this function. F of x equals x to 3/4 when a is 16. So they're asking us to find L of x. Let's write it one more time. So this is f of a plus f prime of a. I'm going to write it like that first. And now all I have to do is replace a by 16. So f of 16 for this problem plus f prime of 16, x minus 16. And this will be a line. It's the equation of the tangent line to the graph of this function at that point. That's all it is. So now we have to find the derivative and plug in 16 here and plug in 16 in the derivative, and we're done. Okay. So then f of 16, this is what I recommend. Of course, you can put in the graphing calculator. 16 is 2 to the 4th. Why did I do that? Because I see power 3/4. And when I multiply the powers, the 4 goes away and I have 2 to the 3rd, which is 8. So this piece is 8. Now I have to find f prime of x. Bring down 3/4 and subtract 1 from 3/4, which is negative 1/4, which reduces to this, the 4th root of x. When I plug in 16 here, the 4th root of 16 is 2. So f prime of 16, I have 3 divided by 8. And I have the equation of the tangent line, of course, called linearization of the function. So L of x is f of 16, 8, plus f prime of 16, 3/8, times x minus 16. I have to simplify it. So the next step would be 8 plus 3/8x minus, I simplify, I get 2 times 3 is 6. 8 minus 6 is 2. 3/8x plus 2. This function very nicely approximates this function for any x value near 16. Now, if you want to approximate near 20, you have to create another line with f of 20, f prime of 20, x minus 20, which will be a different line. Not this. But if you want to approximate, and you're happy with a little bit of error, at 16.3 or 15.7, you can use this. And we can show that. So how will you illustrate that just to convince ourselves? So I'm going to punch in both the function itself, x to 3/4, power 3/4, and the other function, which is 3/8x plus 2. 3 divided by 8 x plus 2. So when we plug in 15.7, see how good of an approximation. This is the tangent, and this is the function itself. What about 16.8? 8.2982 versus 8.3. But if you say, okay, what about 22? Oh no. It happens, but for this function, because it doesn't increase that fast, that is not that far. But at 22, we have to determine a different line using 22. F of 22 plus f prime of 22. You will see that this is a very important concept when you get to Taylor series in Calc 2. Okay? Good. So,
Can you go
yes?
process on how you did that again? Because I don't know where all those numbers came from.
What numbers?
Not on the calculator.
Oh, not with the calculator?
Yeah, on the the 2/4, the 3/4. Where did we get the that?
So I determined f of, this is the function, x to 3/4.
Okay, yeah, I get that.
So when I plug in 16, I get 8. When I differentiate this function, I bring down 3/4, subtract 1 from the power. When I plug in here 16, the fourth of 16 is 2. 2 times 4 is 8, so it's 3/8.